There is a sunrise you have never seen. It did not happen over any ocean, nor did it break across any mountain peak. It was a sunrise on the grandest scale imaginable. A dawn that broke not over a single world, but over the entire universe. For hundreds of millions of years after the Big Bang, there was no light. There were no stars, no galaxies. There was only a cold, dark, and transparent fog of hydrogen and helium gas, expanding endlessly in a silent, featureless void. This was the cosmic dark age, an era of profound universal blackness. The question that has haunted humanity since we first looked up is simple. How did that darkness end? What did it look like when the very first star ignited? A tiny pinprick of fusion in an infinite ocean of night. What did it sound like, in the language of physics, when the very first galaxy swirled into existence, its gravitational pull a silent symphony of creation? To see this event, to witness the universe turning on its own lights, has been the single greatest quest in modern astronomy. It has required us to build a machine of impossible complexity. A time machine with a giant golden eye, designed to do one thing: journey back to the edge of creation and watch the very first sunrise. To understand the scale of this journey, we must first understand our own. For most of human history, the universe was small, intimate, and designed for us. We believed we lived at the center of everything. The stars were fixed points of light on a celestial sphere, a crystal dome that turned above our heads. The sun, the moon, the wandering planets, they were the actors on this divine stage. This was a comforting thought, a cosmology that placed humanity at the very heart of meaning. The model, perfected by the Greco-Roman astronomer Ptolemy, was elegant, mathematically sophisticated, and profoundly wrong. It would take 1,500 years for that illusion to begin to crack. It began with a Polish astronomer, Nicolaus Copernicus, who dared to propose that the Earth was not the center, the Sun was. This was not a small adjustment, it was a demotion. It cast humanity out from the center and set our world adrift, just one planet among others, orbiting a star. Galileo Galilei, with his newly constructed telescope, would deliver the evidence. He saw that Jupiter had its own moons, proving that not everything orbited the Earth. He saw that Venus had phases, just like our moon, a phenomenon that was only possible if it orbited the Sun. With every new observation, the universe grew larger, and our place within it grew smaller. Telescopes improved. Astronomers like William Herschel began to systematically map the heavens, and they noticed something strange. Among the sharp points of starlight were faint, fuzzy patches of light, which they called nebulae, Latin for clouds. Some, like the Great Nebula in Orion, were clearly glowing clouds of gas where new stars are being born. But others were different. They were spiral-shaped, like celestial whirlpools. What were they? Were they solar systems in the process of formation within our own Milky Way? Or were they something far, far grander? This question became the subject of one of the most important debates in scientific history, the Great Debate of 1920. On one side, Harlow Shapley argued that the Milky Way was the entire universe, and these spiral nebulae were simply objects within it. On the other, Heber Curtis argued that they were island universes, entire galaxies just like our own, but at unimaginable distances. The debate was fierce, the evidence on both sides compelling but inconclusive. The universe hung in the balance. Was it one grand galaxy, or were there countless others? The answer would come just a few years later, delivered by a man named Edwin Hubble. Using the colossal 100-inch Hooker telescope at Mount Wilson, the most powerful in the world, Hubble pointed his instrument at the largest of these spiral nebulae, the Great Nebula in Andromeda. And he looked for a specific type of star, a Cepheid variable. These stars have a remarkable property. The rhythm of their pulse, the rate at which they brighten and dim, is directly related to their true, intrinsic brightness. They are cosmic yardsticks. Night after night, Hubble took photographic plates of Andromeda, and then he found one, a single, pulsating star. By comparing its apparent faintness in his telescope to its true, calculated brightness, he could determine its distance. The calculation he made would forever change our world. The Cepheid variable, and therefore the entire Andromeda Nebula, was nearly 1,000,000 light-years away, a distance so vast it placed it far outside the known boundaries of the Milky Way. Heber Curtis had been right. The spiral nebulae were island universes. The Milky Way was not alone. Our one grand galaxy was just one among billions. In a single stroke, the known universe expanded 100 billion-fold. Humanity was no longer at the center of the solar system. Our solar system was not at the center of the galaxy. And now, our galaxy was just a tiny, insignificant speck in an endless ocean of other galaxies. This was a humbling, terrifying, and exhilarating realization. But this discovery, as monumental as it was only the beginning. For Hubble was about to find that this vast ocean of galaxies was doing something impossible. It was growing. The revelation that our Milky Way was just one of countless galaxies was a profound reordering of our place in the cosmos. But the universe was not finished humbling us. Edwin Hubble's discovery was merely the first act in a far stranger play. The second act had already begun years earlier with the quiet and meticulous work of Slipher. While Hubble was focused on distance, Slipher was a master of motion. Using the Lowell Observatory's spectrograph, he had spent years painstakingly measuring the light from those faint spiral nebulae. He had discovered that their light was almost universally stretched, shifted towards the red end of the spectrum. This is redshift, and to understand it is to understand the language of the universe itself. Speaking head, think of the sound of an ambulance siren. As it races towards you, the sound waves are compressed, raising the pitch. As it speeds away, those same sound waves are stretched, lowering the pitch. This is the Doppler effect. Light, being a wave, behaves in precisely the same way. If a star or galaxy is moving towards us, its light waves are compressed, shifting them towards the bluer, higher energy end of the spectrum. If it is moving away, its light waves are stretched, shifting them to the redder, lower energy end. Slipher's data was unambiguous. Nearly every galaxy he measured was redshifted. They were all rushing away from us. But why? Were we at the center of some great cosmic explosion, a point of cosmic repulsion? The idea seemed to violate the very principle Copernicus had taught us, that we hold no special place in the universe. It was Edwin Hubble, in 1929, who put the two pieces of the puzzle together. He took his groundbreaking distance measurements and plotted them against Slipher's redshift data. The result was a graph that would become one of the cornerstones of modern science. A simple, elegant, straight line. The farther a galaxy was from us, the greater its redshift. The farther away it was, the faster it was speeding away. This was the Hubble-Lemaitre law, and its implication was staggering. The universe was expanding, but it was not expanding in the way we might imagine, like shrapnel flying out from an explosion into a pre-existing, empty space. This was far stranger. Space itself was expanding. The very fabric of space-time was stretching, carrying the galaxies along with it. The best way to visualize this is to imagine baking raisin bread. As the dough rises and expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others appear to be rushing away. The farther away a raisin is, the more dough there is between them to expand, and so the faster it appears to recede. This is our universe. We are on one raisin, in one galaxy. And from our vantage point, every other galaxy is being carried away by the expansion of the cosmic dough. This means we are not at the center. In an expanding universe like this, there is no center. Every point is, in a sense, the center of the expansion. This elegant idea finally explained Slipher's observations while preserving the Copernican principle. But it also led to an unavoidable, and at the time, terrifying conclusion. If the universe is expanding today, it must have been smaller yesterday, and the day before that. And if one were to run the cosmic clock backwards, all of the matter and energy in the entire vast universe must, at some point, have been compressed into a single, infinitesimally small, unimaginably hot and dense point. This was the beginning, a day without a yesterday, as the Belgian priest and physicist Georges Lemaitre, who first proposed the idea, called it, a moment of creation, the Big Bang. For decades, this idea remained a compelling but unproven theory, a mathematical ghost. How could we ever prove it? How could we see a moment that happened billions of years in the past? The answer, as it turned out, was not to look for the fire, but to listen for the echo. In the 1940s, physicists like George Gamow reasoned that if the universe began in such a hot, dense state, it must have been saturated with intense radiation, a brilliant fireball of light. As the universe expanded and cooled, that primordial light would have also expanded, its wavelength stretching from high-energy gamma rays to X-rays to visible light, and eventually, far beyond, into the microwave portion of the spectrum. Gamow and his colleagues predicted that this ancient light, this afterglow of creation, should still be detectable today. It should be everywhere, a faint, low-energy hum filling all of space, a whisper from the dawn of time. But for years, no one could find it. The discovery, when it came, was a complete accident. In 1964, at Bell Telephone Laboratories in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were using a massive horn-shaped antenna to study radio signals from the Milky Way. But they had a problem, a persistent, annoying background hiss that they simply could not eliminate. No matter where they pointed their antenna, the hiss was there, a constant, uniform noise coming from every direction in the sky, day and night, season after season. They thought it had to be a problem with their equipment. They rechecked every wire, every connection. They considered radio interference from nearby New York City. At one point, they famously climbed into the antenna and cleaned out what they called a white dielectric material, pigeon droppings, thinking it might be the source of the noise. But nothing worked. The hiss remained. It was a cosmic mystery, an infuriating puzzle for two scientists who simply wanted a clean signal. Meanwhile, just a few miles away at Princeton University, a team of physicists was building their own detector, with the express purpose of finding Gamow's predicted afterglow. Penzias happened to mention his team's mysterious noise to a colleague, who put him in touch with the Princeton group. The conversation that followed would change science forever. Penzias described the uniform, persistent hiss. The Princeton physicists listened, and they knew immediately what the two astronomers had found. They had stumbled upon the echo of creation. The hiss wasn't noise from Earth or from pigeons. It was the cosmic microwave background, the oldest light in the universe. It was the faint, cooled-down remnant of the Big Bang's fireball, a signal that had been traveling across the cosmos for 13.8 billion years, just waiting to be detected. Penzias and Wilson had found the definitive proof of the Big Bang. This was not a theory anymore. It was an observable fact. The light they had found was a baby picture of the universe, a snapshot taken when it was just 380,000 years old, the moment when the primordial fog finally cleared and light could travel freely for the first time. But this picture also revealed the edge of a great, dark curtain, for before that moment the universe was an opaque wall of plasma, and for hundreds of millions of years after it, it was a transparent, but empty, darkness. The cosmic dark ages. The baby picture of the universe, the cosmic microwave background, is the oldest light we can ever hope to see directly. It is a wall of light, a snapshot of the moment the cosmos became transparent. But in becoming transparent, the universe also became dark. The brilliant light of the primordial fireball was now stretched and faded, redshifted into the invisible microwave spectrum. The universe was now a cool, expanding, and utterly dark place. This was the beginning of the cosmic dark ages. For hundreds of millions of years, an unimaginable span of time, nothing happened, or rather, nothing luminous happened. The universe was a simple, almost featureless place, composed of a vast, thin fog of hydrogen and helium gas left over from the Big Bang. There were no heavier elements. No carbon, no oxygen, no iron. Those are forged in the hearts of stars, and there were no stars. There were no planets. No galaxies. There was only the gas, the darkness, and the patient, inexorable work of a single force, gravity. But the universe was not perfectly uniform. That baby picture, the CMB, showed us that. There were tiny, almost imperceptible fluctuations in temperature and density, variations of just 1 part in 100,000. These minuscule imperfections were the seeds of everything to come. They were the gentle slopes in a vast, flat landscape. And just as water will always trickle downhill, gravity began its slow, silent work. Over millions upon millions of years, gravity gently tugged at the gas, pulling it from the slightly less dense regions and gathering it into the slightly more dense regions. It was a process of cosmic accretion on an epic scale. Filaments of gas began to form, creating the first faint outlines of a great cosmic web. At the intersections of these filaments, where the pull of gravity was strongest, vast clouds of hydrogen began to coalesce, growing ever larger, ever denser, ever more massive. This was the invisible construction phase of the universe, the silent gathering of the materials for creation. Inside these collapsing, darkening clouds, the pressure and temperature began to rise. A battle was being waged between the inward crush of gravity and the outward push of gas pressure. For hundreds of millions of years, gravity was slowly, patiently winning. The universe was holding its breath, waiting for a spark, waiting for a critical threshold to be reached, for the temperature and pressure at the heart of one of these collapsing clouds to become so immense that the very atoms of hydrogen would be forced to fuse together. This is the edge of our knowledge. This is the great, dark curtain that separates our modern, light-filled universe from its ancient, dark past. What happened next? How did the first star, a star made of pure primordial hydrogen and helium, finally ignite? What did it look like? How big was it? And how did that single act of creation, the first light since the Big Bang, trigger a chain reaction that would end the Dark Ages and set the entire universe ablaze? To answer these questions, we could no longer rely on listening for faint, ancient echoes. We needed to see it for ourselves. We needed to build a telescope so powerful it could look back across 13.5 billion years of expanding space and capture the faint, redshifted light from that very first spark. We needed to build a time machine, to see the invisible, to witness the birth of the first stars. Humanity needed a new window on the universe. Our view from the Earth's surface had always been compromised. We live at the bottom of a deep, turbulent ocean of air. The atmosphere, the very thing that gives us life, is a shimmering, blurry veil that distorts and blocks the faint light from distant galaxies. To get a truly clear view, we had to go above it. We had to put a telescope in space. This was the dream that would become the Hubble Space Telescope. Rocket launched in 1990, Hubble was more than just an observatory. It was a promise of cosmic clarity. It was the most complex scientific instrument ever built, a school bus-sized marvel of engineering, deployed into the unforgiving vacuum of low Earth orbit. Its mission: to see the universe with 10 times the resolution of the best ground-based telescopes, to resolve the great questions of its age, and to show us our cosmos in all its breathtaking glory. But the promise was almost broken. The first images returned were a crushing disappointment. They were blurry, unfocused. A microscopic flaw in its main mirror, an error of just 2 microns, less than the width of a human hair, had turned the world's greatest telescope into a symbol of spectacular failure. But the story of Hubble is a story of human ingenuity and perseverance. In one of the most daring and complex space missions ever attempted, a team of astronauts flew to the telescope in 1993 and installed a set of corrective optics, essentially giving Hubble a pair of eyeglasses. And suddenly, the universe snapped into focus. The promise was fulfilled. For the next 3 decades, the Hubble Space Telescope would revolutionize nearly every field of astronomy. It helped us determine the age of the universe with unprecedented accuracy. It provided the first conclusive evidence for the existence of supermassive black holes at the centers of galaxies. It watched comets collide with Jupiter, observed the weather on distant planets, and charted the mysterious force of dark energy, the strange anti-gravity that is accelerating the expansion of the universe. But its most profound legacy, the one that would set the stage for its successor, came from a single audacious observation. In 1995, astronomers decided to do something that sounded absurd. They pointed Hubble at a patch of sky near the Big Dipper that was completely, utterly empty. A region so dark and barren that it was thought to contain nothing at all. For 10 consecutive days, Hubble stared into this abyss, collecting every single photon of light that trickled in. The result was one of the most important images in human history: the Hubble Deep Field. The black, empty patch of sky was not empty at all. It was teeming with galaxies, 3,000 of them, each a city of billions of stars. Galaxies of every shape, size, and color. Some were grand, mature spirals like our own. Others were chaotic, irregular smash-ups, caught in the act of colliding. And some were small, faint, red smudges, the most distant galaxies ever seen at the time, their light having traveled for over 12 billion years to reach us. Hubble had looked back in time. It had shown us the universe in its adolescence. With subsequent, even deeper observations, like the ultra-deep field, Hubble pushed the limits even further, capturing galaxies from when the universe was less than 1 billion years old. It was a triumph. But even in its greatest moment, the deep field revealed Hubble's fundamental limitation. It was hitting a wall. A red wall. The faint, red smudges of the most distant galaxies were at the absolute edge of its vision. It could see the universe in its late childhood, but it could not see its infancy. It could not see the dawn of time. The problem, once again, was redshift. The very same expansion of space that allowed Hubble to measure the universe was now hiding the universe's earliest chapters from it. The light from the very first galaxies, the ones that ignited in the cosmic dark ages, has been traveling for over 13 billion years. For its entire journey, it has been stretched by the expanding fabric of space-time. The brilliant, high-energy ultraviolet and visible light that those first stars emitted has been so profoundly redshifted that by the time it reaches our solar system, it is no longer visible light at all. It has been transformed into the invisible light of the infrared spectrum, heat radiation. Hubble is an optical telescope. Its detectors are designed to see the same kind of light our eyes do. It can see a tiny sliver of the near-infrared, but it is fundamentally blind to the deep infrared universe, where the secrets of the first stars are hidden. To see the dawn of time, we needed an entirely new kind of observatory. We needed a telescope that could see in infrared. And that presented a new, colossal challenge. To see the faint infrared heat from the edge of the universe, the telescope itself had to be unimaginably cold. Hubble had taken us to the edge of the visible universe, but the dawn of time remained hidden behind a veil of infrared light. To pierce that veil, astronomers knew they'd need a new kind of eye in the sky. The dream of Hubble's successor began long before Hubble itself was even launched. In the late 1980s, at the Space Telescope Science Institute, a workshop was held to imagine the next great leap. They called it, simply, the Next Generation Space Telescope. The dream was audacious. They wanted a telescope with a mirror, at least 4 times the size of Hubble's, capable of seeing the very first galaxies. But they knew that building an infrared telescope in space would be one of the most difficult engineering challenges ever undertaken. The challenge is heat. To us, heat is a feeling. To an infrared telescope, heat is light. It's a blinding, deafening roar that can easily drown out the faint whispers from the edge of the universe. The telescope itself, its electronics, its mirrors, if they're even a little bit warm, they'll glow brightly in the infrared, blinding the very instruments they're meant to serve. It's like trying to take a photograph of a distant candle while the inside of your camera is on fire. This fundamental problem meant the Next Generation Space Telescope had to meet 2 non-negotiable conditions. First, it had to be cold. Incredibly cold. Colder than any natural place on the surface of the Earth. It would need to operate at a temperature below 50 Kelvin, that's minus 223 degrees Celsius, or minus 370 degrees Fahrenheit. Second, to collect the impossibly faint and stretched out light from the first galaxies, it had to be enormous. Its mirror would have to be a giant light bucket, many times larger than Hubble's. And these 2 requirements, to be both huge and freezing cold, would dictate every single decision for the next 30 years. The first casualty of these requirements was Hubble's home. Low Earth orbit, just a few hundred miles up, is a warm and cozy place. The Earth fills half the sky, bathing everything in its reflected sunlight and its own infrared glow. A sensitive infrared telescope there would be like trying to stargaze from the middle of Times Square at noon. A new location was needed, a place far from the Earth's warmth, a place of perpetual deep space cold. The destination they chose was a place called Lagrange Point 2, or *2. It's a peculiar miracle of celestial mechanics. A point in space, 1.5 million kilometers, or nearly 1 million miles, away from Earth, in the exact opposite direction from the Sun. At this precise point, the gravitational pull of the Sun and the Earth combine in just the right way to allow an object to orbit the Sun in perfect lockstep with the Earth. From the perspective of the telescope at L2, The sun, the earth, and the moon would always be in the same direction, allowing it to keep its back turned to their heat and stare uninterrupted into the cold, dark abyss. This distant, lonely outpost in the solar system was the only place the observatory could fulfill its destiny. With the location chosen, the second, even greater challenge came into focus: the mirror, the light bucket. To be powerful enough to capture the faint flicker of the first stars, astronomers calculated it needed a primary mirror at least 6.5 meters, or 21 feet, in diameter. Hubble's mirror, by comparison, is 2.4 meters. This new mirror would have a collecting area more than 6 times larger. But this presented a seemingly insurmountable problem. A 6.5-meter mirror, built as a single piece of glass, would be far too heavy to launch on any rocket. And even if it were weightless, it would be too wide to fit inside any existing rocket's protective nose cone, its fairing. The dream of a giant mirror seemed destined to remain a dream. The solution was not to build a single monolithic mirror, but to build one from many smaller pieces, like a mosaic. A segmented mirror that could be folded up like a piece of cosmic origami to fit within the rocket, and then unfolded with perfect precision in the cold of deep space. The final design called for 18 hexagonal segments, each one a technological marvel in its own right. They would be arranged in a honeycomb pattern, a design that is both incredibly strong and efficient. But what would these mirrors be made of? Glass, the traditional material for telescopes, would shrink and warp too much in the extreme cold of L2. A new material was needed.